Good afternoon. Today we're going to look at analysis methods for fatigues of welds using DesignLife. I want to start with just a brief overview on weld analysis, some of its challenges and particular aspects. We'll look at the existing DesignLife seam weld capabilities for shells, and then we'll look at the new solid element support that's been added to DesignLife 9.0. I'll go through a couple of correlation studies looking at the solid weld performance against actual test cases and do a brief demonstration on the software, and then we'll open up for questions. Okay. What we want to do is kind of look at a description of some of the things that drive weld fatigue, and actually, in particular, make it difficult. Most times, we look at a fatigue process where we utilize very detailed material properties, geometry descriptions, and loadings to go off and do a fatigue analysis. When we're looking at welds, that becomes not practical in most cases because we now have a geometry that is very difficult to describe in a finite element model. We have aspects of the weld such as the deposited metal from the weld, a heat affected zone around that has changed the base metal material properties. We have residual stresses, many times very large and unknown. And again, we look at the details of the geometry, and we're looking at things that would be virtually impossible to build into an FE model. There's several different strategies for trying to go off and predict weld fatigue. One leverages fracture mechanics. And again, from the previous picture, you can see that at the weld toe, we literally had an existing crack. And so fracture mechanics would make sense here. Some of the downsides to an approach like this is that, one, it's a very point-wise calculation. We would need to have multiple calculations along the entire weld toe, or wherever our weld failure is specified to be. Two, we need to specify the size and shape of the crack as well as its direction. The size is an issue. The initial size for a crack pretty much determines the total life, and so there, with that as somewhat unknown, it's difficult to go off and to utilize fracture mechanics by themselves. There are local approaches, that is, going in and attempting to model the weld in as great detail as possible. Even with this, obviously, we're never going to be able to capture some of the detail that we saw in the weld toe. But here, I could go in and represent reasonably well the toe radius, some of the geometry aspects of the reinforcement, and as well as the penetration of the weld. Look at things like partial penetration. A final approach is using a structural stress or hotspot stress. Here we're trying to capture the stress at the toe of the weld without the effect of the stress concentration of the toe. And this can be done in a variety of ways, be it nominal stresses or extrapolated stresses away from the toe. But this is actually the approach that we're going to, we actually already use in DesignLife in terms of grid point forces and shells, and the same type of approach will be used for the solids. Many methodologies, be them both design codes as well as fatigue prediction codes, utilize this technique. So things such as the British Weld Standard and Euro Code and the ASME pressure vessel code all utilize structural stress methods in one form or another. And again, the Volvo method, or the existing seam weld method that we utilize inside DesignLife for shells, does the same thing. And again, these structural stresses are an attempt to obtain the stress at the toe of the weld without the effect of the stress concentration. And again, it could be as simple as a nominal stress calculation adjacent to the weld toe. It could be a hotspot stress where we have extrapolation, or in the case of the shell elements inside of DesignLife, it could be utilizing grid point forces, going off and taking the grid point forces in moments and just calculating a stress from that, nothing more than just P over A, MC over I style calculations. The fact that we're utilizing stress measures that don't represent the actual stress at the toe leads us to go in and use a damage curve that isn't really talking about material. We're not going to have a damage curve that's looking at the fatigue effect of the deposited weld metal or the heat affected zone. What we do is we're going to take a page from the initial investigations into fatigue, and we're going to develop what we term as a component SN curve, or stress life curve. Here, as in Wooler's experiment on the left-hand side, he actually developed design curves using his actual railroad axles. Those curves aren't material properties of steel or cast iron. Rather, they contain every aspect of the fatigue performance from his axle. Residual stresses, stress rises such as the shoulder fillet in his axle, anything in terms of surface finish effects, all are embedded inside that SN curve. We're going to do exactly the same thing for our weld curves. So we end up starting with test specimens. Those test specimens now will give us load life curves, and from that and a transfer of load to stress using our FE models, we're able to create these stress life curves we're going to use for our weld analysis. Again, these curves don't represent the weld behavior, the weld material behavior, as in the deposit metal or heat affected zone. They're actually describing the weld itself, as if it were a part. As I had mentioned, DesignLife has had the ability to do weld analysis on shells for many releases. And the hallmark of it basically is ability to go off and represent the welds in the parts as a relatively coarse shell mesh. A meshing approach that would allow us to go off and deal with literally hundreds of welds in a structure and be able to model an entire structure. Again, we're utilizing structural stresses. There are several methodologies in DesignLife for that. We're going to focus in on the grid point force and moment approach. That was the original approach from the initial paper back in 1998, and again, it is a recommended approach today. We'll look at the damage curves that we use. Again, these are generic curves that represent welds. We basically have a curve definition for steel, one for aluminum, and we're basically going to go off and use that curve definition to describe all the welds we look at in terms of steel, or all the welds we look at in terms of aluminum. In order to go off and to successfully have a generic curve, a single curve to describe this, there are several corrections that we'll need to apply to basically kind of normalize our behavior. One, we're going to look at bending ratio corrections that we will utilize to determine what loads cause the stresses. We'll look at thickness corrections. Again, we need to have some way to normalize the parts based on thickness. And we'll also look at mean stress corrections that are available within the seam weld capability. I've already mentioned that the shell methodology utilizes structural stress calculations. The original calculations were grid point force and moments actually centered at the node points along the toe elements touching the weld. So the overall methodology in terms of meshing, on the left-hand side you see a representative mesh. The elements in green represent the weld elements themselves, and they're presented to DesignLife basically just to identify the weld. Their purpose in the overall modeling is to transfer the load from one part to the next. The elements that are highlighted in red and in blue are actually the toe and root elements that are identified because of their connection to the welds. Those are the elements that we will recover the stresses from. And in the original technique, the stresses were recovered at the nodes, and the node point forces and moments were used to calculate the structural stresses. In the current release of DesignLife, we've modified the technique somewhat in that we now we're recovering the grid point forces and moments, but we actually then go in and average them to the center of the toe edge. So now we're actually calculating, if you will, basically a uniform stress across the entire toe edge. This was actually done for a couple reasons, but looking at the performance of averaging the structural stresses across the element edge brought benefits in terms of reducing the false positives or the excessively high damages that sometimes occurred at weld ends. Again, we're calculating structural stresses. These are stresses that don't necessarily occur anywhere in the model, and are definitely not the actual stresses at the weld toe. But they are the stresses that we're going to utilize as a damage parameter. They were selected because they show a fair insensitivity to things such as mesh distortion and mesh density. To go off and to produce the damage curves for this is a several-step process. First off, actual test specimens are analyzed load life fatigue. And in the case of DesignLife, the original specimens were a series of rectangular welded joints as well as hydroform sections, including both continuous weld as well as skip weld configurations. And these all were tested for fatigue and generated a family of load life curves. Because of the different sizes of the specimens, thicknesses of the specimens, the load life curves were basically scattered across a wide range. Each of the specimens are then analyzed in FE using the meshing technique we had just seen, where we have a simple shell element that represents the weld, and stresses are recovered using the structural stress methods. Using the FE model to basically convert load life to stress life, we see that we end up having, in essence, two sets of behaviors. If you look on the right-hand side of the PowerPoint, you'll see that we actually have two SN curves. The upper one in red represents the behavior of welds that were primarily in bending. So any time that a weld was sitting, as you see in the model up there, basically on a flat plane, and that part was loaded, that weld went primarily into bending. The lower curve is a representation of the behavior of welds that were primarily in tension or in membrane. And so in the lower model, the tubes all have the same width, such that the welds themselves, when loaded, are primarily in tension. Now, this tends to make sense when you go back and think of the fact that we're recovering stresses, these structural stresses, and those are used basically as just a damage parameter. However, the actual stress at the toe of the weld or at the root location is typically much higher because of the detailed geometry. If one goes back in and looks at the application of things such as elastic stress concentration factors, besides the stress concentration geometry, the loading mode is also important. And so what we're seeing here is the impact of the loading mode on generating these stresses. Now, the way we utilize these inside of DesignLife is we actually left both curves, the red curve representing the fatigue behavior at 100% bending stress, and the blue curve at 100% membrane stress. And then internally, at each location where we're analyzing the weld fatigue, we calculate a bending ratio. This is nothing more than the bending stress divided by the total stress. And that bending ratio is used along with an interpolation curve to go in and to basically interpolate a new SN curve. And again, this is just some linear combination of the flexible curve and the stiff curve to match the bending ratio at each location. So we're basically going to synthesize an SN curve at each location based on the amount of bending and membrane stress that actually comprises the overall stress state. There are a couple more corrections to the stress state. One involves thickness. Again, when we went back and looked at our test specimens, besides having a range of part sizes, they also had a range of sheet thickness comprising the parts. In order to go in and to generate a single curve definition across all those thicknesses, what we do is we normalize the stress based on the thickness correction that you see in the upper left-hand corner. In DesignLife, we've just assumed a reference thickness of 1 millimeter. And if we take the actual part thickness divided into the reference thickness to this exponent, we use that correction against the stresses to give us a normalized stress. Within DesignLife, the correction exponent is set to 1/6. And so this overall correction was used to take all the specimen data and to normalize it such that we had a reference. Our curve inside the database was set to 1 millimeter. However, when you go in and analyze an actual part, we use this correction in reverse to go in now and to come up with an effective stress due to whatever the actual thickness of our part is. There's a second correction that's also available, and that's actually a mean stress correction on the stresses from the loads. Many times when you look at weld fatigue, we tend to ignore the mean stresses from the loading because as part of the welding process, residual stresses are left in the weld that many times can approach yield. Because I have these very high residual stresses, the mean stresses from the actual loading tend to be relatively unimportant. However, DesignLife, the seam weld technique in DesignLife originated with very thin structures, body structures, many times thicknesses even sub-millimeter, and structures made of materials of that gauge don't really have the ability to maintain these high residual stresses after welding. So those residual stresses tend to wash away, making the mean stresses from the actual loading important. Because of that, a mean stress correction was added to the seam weld technique, and it utilizes a constant life curve that you see displayed on the lower right-hand side that is defined from the FKM fatigue guidelines. So this is nothing more than a constant life diagram. However, the FKM curve actually is a little more sophisticated than some of the ones we're familiar with, like Goodman and Gerber. This actually has 4 separate slopes that define the constant life. Again, the thickness corrections can be turned on or turned off. They should almost always be on. The mean stress corrections, however, can be, again, deactivated, and I probably would do that on parts that have thicknesses, over a couple millimeters or more. Those stress recovery techniques, material definition, and corrections to the stresses are all part of the original seam weld technique defined for shells. At 9.0, we've actually added support to deal with solid elements as well. And this was done for several reasons, but as much as anything, there are just applications where the part is not easily modeled with shells. I mean, an approach where I go in and model with shells, I have to make some sort of idealization or assumptions to come up with appropriate shell model, and some structures just really aren't applicable to shell modeling. In addition, what I'm showing here in gray is a representative solid mesh of a lap shear specimen that was done by the Steel Partnership. And what you see in terms of the shell mesh kind of overlaid on that, just the mid surfaces there, that basically the 2 shells in purple and red and the weld in cyan, is the shell representation of the weld. As you can see, the actual weld geometry, the only part of the weld geometry that's actually captured in shell modeling is really the location of the toe and the root. The overall description of the reinforcement, the amount of penetration of the weld are pretty much lost with a shell model. A solid model, however, gives us the ability to capture that. So I can actually have a more detailed description of the actual weld, showing degrees of partial penetration, showing geometry on the reinforcement, and have some of that affect my weld behavior. Secondly, we actually haven't really invented anything here. On the shell representation, we're using grid point forces and moments to calculate structural stress. We do not do that for the solids because of really the complexities of generating an FE model and using that kind of approach. However, we did take a approach that has been prescribed by the boiler code, the ASME boiler and pressure vessel code, to do stress linearization. And the major reason for that is the fact that we can now apply that to kind of an arbitrary mesh independent of node element arrangement. The overall technique starts with a model where I have a weld I want to analyze, and all we really need to do for DesignLife is describe the location where I want to do this weld calculation. So here I have that coordinate system that you see, and the origin of that coordinate system is just a location in space where I actually want to do this analysis. Again, that location doesn't have to necessarily be a node location or on an element edge. It's just a location in space, relatively close to the surface in question. The other input for this is just a vector. Here you see a VN is a normal vector that's going to describe the direction opposite where I want to drill through the solid to do the linearization. With these two, we actually go in, find a location on the surface of interest, again, a location close to the origin of that coordinate system. We also find a location on the opposite surface. So we're looking for a free surface where this line where we drill down through will penetrate, pierce the opposite surface. And then from those two starts, to starting in any locations, we specify a series of points where we're going to evaluate the stress. This is a user-defined number. Here I'm showing 4. By default, the software is using 15. But these are equally spaced locations where we can have DesignLife go in and interrogate at that location, which element am I in? Once he knows the element, he can go off and specify, well, where am I in that element? And then once I know where am I in that element, I can ask, what is the stresses? And we can calculate then at each one of those locations the actual stresses. And the stresses that we're calculating here are basically a 2D stress tensor that would be in plane perpendicular to the normal that we're going through. So we would be calculating, in essence, a local sigma x, sigma y, tau xy at each one of those locations. And again, those planes would be a plane perpendicular to the stress linearization line. Once we have the actual stresses at those locations, we use the equations you see in the upper right-hand side. The top equation is literally nothing more than going off and coming up with an area average of the stresses from all those locations to give us a tension stress. And again, that tension stress would be literally a uniform stress for sigma x, a uniform stress for sigma y, and a uniform shear stress, tau xy. The lower equation is going off and recovering the bending stresses, the linearized bending stresses through the thickness. And again, this is actually done for the 2D stress tensor, sigma x, sigma y, tau xy. When we're done, we now have a uniform membrane stress profile across the whole section, as well as a linearized bending stress profile. Again, at this point, these stresses are still stress tensors. So I have a sigma x, a sigma y, tau xy, and we're able to then go in and just by summing the two, we now have a stress state for the top of the solid model as well as the bottom. We'll see in just a bit that we can then go off and evaluate the stresses in a variety of ways. The purpose of this work is to actually allow us to go in and to, again, obtain a stress at the toe of the weld that is independent of the stress concentration of that toe. Here I have 4 models, the same overall geometry with different element types and mesh densities. The upper right-hand corner, I have 20 node bricks. The upper left-hand corner, I'm sorry. The upper right-hand corner, I have 10 node tetras in a relatively fine meshing scheme. The lower left-hand side, I have 10 node tetras in a relatively coarse meshing scheme. And then the lower right-hand corner, I have linear bricks in a moderately fine meshing scheme. If I were to go off and look at detail at the stresses at the toe, and again, the toe has not been modeled, the radius of the toe has not been modeled, so this is more or less a reentrant corner, in essence, a singular stress. I see stresses coming from the 20 node bricks, a maximum stress of 672 along the edge. In the fine mesh for 10 node tetras, I actually have a toe stress of 1600. The coarse mesh I have for tetras, I have a max stress of 896, so close to 900, and then in the linear bricks, I have a toe stress of 695. So you see here, we actually are looking at a range somewhere between 672 and 1600 as a range of stress just due to mesh densities. Taking the stress linearization approach, I can go in and look at the linearized stress at the top. We're going to be looking at the location of the top surface of this lower fillet, and I have calculated linearized stresses of 550, 568, 541, and 552. So even though I do have significantly different mesh densities and element types, the stress linearization gives me a relatively uniform stress measure to use for my fatigue calc. Now, this is a very busy slide, but I brought this up. We had talked about the shell seam weld solution methodology, and this is actually laid out as a flow chart. And just to kind of walk you through it, the lower path here in blue is a calculation at the location where I want to evaluate the stress and hence the fatigue. And it's walking through generating a stress history, modifying that stress history for thicknesses, and then eventually for mean stresses. Along the top, there is a stress that's recovered basically in the same orientation on the bottom as I have on the top, and this stress is used to calculate the bending ratio. Again, if I have a top stress and bottom stress, the average is my membrane stress, the difference is my bending stress. So along the top path, I'm looking at the bottom stress in the same direction as the top stress and using that to calculate my bending ratio. And once I have a bending ratio, I can go in and use the fatigue curves to interpolate and get a unique fatigue curve for this bending ratio, and that's used with the stresses along the bottom. So this is the overall path. And all we've actually done in this particular implementation is we've basically now replacing the stresses that come in. Instead of being shell stresses recovered top and bottom, they're the linearized stresses that we basically go off and calculate a effective top and effective bottom stress. So the rest of the methodology in the fatigue calculation is the same with the solids. That's with this release. This methodology actually gives us avenues into doing the exact calculations out of the pressure vessel code, or using it for other techniques as well. But in the version 9 implementation, we're taking the linearized stresses from solids and using them along the same path that we've used for the shells. The actual weld definitions are completely geometry based. When we define these weld locations, there's no reference to nodes or elements. DesignLife actually takes just physical locations in space and directions and uses that to identify locations on the surfaces, top and bottom of the plate to be welded, as well as identifying all the locations interior and being able to calculate the stresses at those locations by interrogating the model and figuring out which element is involved and what location in the element. This actually is seen to have a lot of advantages in that ideally where we see this weld definition file coming from is most likely a CAD system, a design system where the welds are part of the design geometry, and we can go off and interrogate the CAD model and get the locations and the relative surface normals. Currently, no mechanism has been actually put into DesignLife to calculate this file. This file is actually brought in. We are in the process of developing a couple interfaces to preprocessors, not really the CAD system currently, but finite element preprocessors to allow us to generate this file via representations via surface curve or node element face representations. But this file is actually imported into DesignLife to define our weld paths. And finally, looking at the solid versus shell. On the shell approach, one of the things that was done initially was to predefine the failure locations. So with the shell weld definitions, we had this concept of a fillet weld where the plates were relatively perpendicular to one another, overlap weld where they're relatively parallel, and we predefined the failure locations as you see here. You know, basically on a fillet weld, the failure locations were defined to be the weld toes cracking down through the heat affected zone through the bottom plate and through the upper top plate, as well as a root failure location as well. But these were predetermined and hard-coded in the technique. In the solid technique, the user defines the direction to do the stress linearization, and the stress linearization basically defines the failure path. So here, what we're looking at is a weld, and the horizontal plates are actually two plates that are basically loaded in tension. So these are two separate plates, and the connection between the two plates now is a common weld with a small vertical riser plate. If one goes off and looks closely here, you'll see that the weld actually only represents a portion of the connection, and actually the base of the horizontal plate is not physically connected to the vertical plate at all. So this basically is a partial penetration weld. We can go in and represent the weld path the same way it would have been done in shells, and that is taking a weld toe and basically driving down from the weld toe through to the plate bottom. The same thing for the vertical plate. But in addition, we have the ability to go off and define additional weld paths. And so here we've picked three basically trajectories going through the throat. One going basically along the junction of the weld and the vertical plate, one going right through the center of the weld throat, and a third one going basically at the junction of the horizontal plate in the weld. All of these are then going to be analyzed by the program. So what we're looking at here is just looking straight down the cross-section of that weld path. Here you can see a little better where we do have the gap built into the model where we have no weld penetration. And what you're looking at are markers that define the weld results. Because these welds are not attached to actual nodes or elements, we needed some sort of mechanism to display the weld location as well as the results. And so these markers start out, the fat end actually is a location where the weld initiates, and then they are basically pointing in the direction of the stress linearization line, and their length represents the length of the line that was calculated. And here you see we have both the toes as well as the three throat calculation showing here, and in this case actually the one throat calculation is the one that drives the fatigue result. There have been several studies looking at the effect of using this linearization in solids, as well as the impact of element types and mesh densities on this, and we're going to look at a couple cases. Here is a test specimen that came out of a report from the Weld Institute, and they're looking at a partial penetration weld of two rectangular sections. Both these sections have thicknesses around 6 millimeters. You can see the mesh density that was used in this particular analysis in the lower right-hand side. Here, the number of elements through the thickness of the plates are around 3 elements, 3 tetras. Obviously, that's not always uniform, but that's relatively, if you were to go off and take any cross-section, we're probably looking around 3 elements through the thickness. And again, looking at the upper right-hand display, you can see that this is a partial penetration weld. I actually have the two plates being welded, the two tubes being welded, really separated from one another, and the only connection between them is the weld metal. In this particular case, the trajectories were defined to be the weld toes, and in this test case, there were 2 loading modes that were tested in the, well, actually there were 3 loading modes tested. I'm showing 2 of them here. One was an in-plane bending, where the loading was applied basically coaxial with the bottom tube. And there was a second out-of-plane bending, where it was perpendicular to the tube. Looking at the actual test results versus analysis, the upper plot is a display of the life markers coming from the solid welds, and one can see immediately that we're allowed to put a large number of these calculation points along the weld toe. There actually could be multiple locations within a single element if you put them that tightly. And what we're looking at is the life to initiation. Again, the seam weld technique is, the curves for the seam weld technique were derived from the onset of a visible crack. So, in essence, we're looking at initiation. The actual results for the in-plane loading out of the Weld Institute report was the first recorded crack was actually a 15-millimeter crack. And so you see, we predicted a life of 26,000. At 15 millimeters, the life is 70,000. But again, our prediction will be looking at the onset of a visible crack, probably a couple millimeters in length. So that may not be a bad prediction at all. This was in-plane loading, out-of-plane loading. Similar set of results. The lower is looking at the weld profile. The red lines, again, are cracks that were observed initially here at 47,000 cycles. Our initiation prediction here is 43,000 cycles. There are a couple more examples of the Weld Institute report. This one happens to be a continuous plate, horizontal plate that's continuous, and the 2 tubes that you see welded, top and bottom of that plate, are non-load carrying. So the load basically is transmitted through that horizontal plate. Those tubes only interact with that plate in terms of stiffening it. So basically, it's an attachment that's non-load carrying. However, because of the increased stiffness, there is stress rises along the weld toes. And if you look at the XY plot, the markers represent test specimens that were actually tested. The line is the prediction from DesignLife using a solid element mesh of that. Again, mesh densities on this were such that we're probably looking somewhere around 3 elements for the thickness of that plate, at least around the weld. Second specimen, similar configuration where the horizontal plate is continuous. The 2 attachments, that vertical and plate on top and bottom, are simply attachments stiffening the weld. Those stiffeners don't actually go across the entire plate width, so there's a stress riser at the weld end, the plate end there. And again, looking at predictions from the actual physical tests as well as the curve representing DesignLife calculations. And in the region of finite life, they match up fairly well. Final specimen here is the actual specimen we saw earlier on, showing the ability to define paths inside of the solid weld technique. And so here, the horizontal plate is not continuous. There's 2 separate plates. So this is a load-carrying weld. The actual connection between those 2 horizontal plates is the weld itself. And again, the way they're welded is both plates, the left and right side, are welded to that short segment of vertical plate. Again, this weld is not full penetration, so there is a gap between the base of the horizontal plates with respect to the vertical plate. And again, the markers represent actual test specimens, life of test specimens, and the line is the DesignLife solid weld prediction. At this point, I'm just going to bring up DesignLife really quickly and give you an idea how the actual software interacts. I have a process built here already that is set up to do the solid weld. And so I'm going to go in and bring in an FE model. This happens to be one of the specimens from that study I showed you looking at mesh density. So here we actually have two load cases on this model. One is a tension load case, if we look at the stresses for that. So basically what we have here is tension on the lower bar, and the only interaction with the upper bar and the weld is, again, this effect of stiffener, a stress stiffener. We have a second load case that is going in and taking the lower bar and putting it in bending. So here we have a vertical load, and what we see is there's a load path that goes through the weld up the vertical part. So we have two load cases here. Both load cases, we see the impact of the reentrant corner of the weld toe and its high stress. The actual seam weld glyph, this particular glyph has actually been set up for the solid modeling technique, and what that really represents is, besides weld configurations and things like fillet and overlap, there's now a solid. And if we pick the solid weld option, we get three more properties that I've exposed on the properties page of this glyph. And the bottom one is the most important, and that is a pointer to this weld definition file. So I just can go off and go browse, pick that file. And again, this is an ASCII file that's nothing more than specifying locations where I want to do the analysis and directions. And then the last two properties for this are, one, the number of locations, thickness at which I basically stop my line and use that as the opposite end. And so this could be actually on some of the throw calculations I had shown you earlier. The actual weld never exited the plate. It actually was stopped by this max thickness. So those are the three controls. Again, the stresses we're calculating are a full tensor, a 2D tensor, and so we have the option of picking weld normal, ABS max principle, or critical plane combination methods from this. And once I have this, all I need to do is go in and run, and every location that has been defined, and here I had 9 locations on the bottom toe, 9 locations on the top toe, are calculated for things such as life, bending ratio, max stress. Max stress in this case would be the structural stress, this linearized stress at top and bottom that I'm predicting. Other things you'll see is the welds are actually locations independent of geometry, independent of fine element geometry, nodes or elements, and they're grouped together in terms of groups of weld lines. Each weld line actually can have a separate set of properties in terms of fatigue curve properties, as well as things such as the max depth to go through. And then each individual weld calculation point within that line has IDs of its own, so they can be identified. Okay? So with that, let's come back. I'm going to give the mic back to Kim, and we'll open up the session for questions.